Problem 6.7.2. Take a moment to read the question before you go any further. We've got a block sitting on an inclined plane. So let's draw a picture of that. And it's making some angle with the horizontal. Here's our block. And the block is being raised, so sometime later it's at a higher angle, sitting on the block. If I draw a free body diagram for each of these two situations, dashed line representing the incline there, then in both cases I've got mg pulling down, and in both cases it's the same block, so the gravitational force, the earth pulling down on the block, is the same. The normal force for this guy is up there, making the right angle. The normal force for this guy is out that way, making the right angle. So the normal forces are not in the same direction, nor are they the same magnitude. The frictional force, parallel, just call that little f. Here the frictional force goes parallel up there. And if this block is going to maintain its equilibrium, the combined friction and normal force has to be equal and opposite to mg. I just sketch that in. What that means is, because of the way the geometry is changing, the normal force is decreasing. The frictional force we need to maintain equilibrium, as this force gets smaller, the normal force, so the frictional force required to maintain equilibrium has to get larger. But at the same time, the frictional force is proportional to the normal force, which is getting smaller. So we're in this situation where as the angle increases, we need the frictional force to get bigger and bigger in order to hold things in place. And yet, because the normal force is decreasing, the maximum frictional force is actually decreasing. So at some point it's going to break down and the block is going to start to slide down the ramp. The question is, when does that happen? So if we take the forces that we've got and draw the force triangle for equilibrium, it's going to look like this. And if I compare triangles, I'm going to see that this angle here is the same as the angle of incline of the ramp, the theta. So when I look at this triangle, my frictional force has got to be at least as big. It's got to be bigger than my maximum frictional force, F max, has got to be bigger than the F side of this triangle, which, when you do the trigonometry, has to be equal to mg times the sine of the angle, mg sine theta. The other thing we know about frictional forces is that the maximum frictional force is equal to coefficient of friction multiplied by the normal force. And the normal force, again from the triangle, that's mg times the sine, times the cosine, sorry, of the angle, mg cosine theta. So when I combine these two equations, now my maximum frictional force is equal to mu mg cosine theta, and that's going to be greater than or equal to mg sine theta. So putting all that together, mu mg cosine of the angle has got to be greater than or equal to mg sine of the angle. And this is where algebra makes things beautifully simple if you can just stick with it, because m and g all disappear. And this simplifies to the coefficient of friction has got to be greater than or equal to the tangent of the angle. And there you are.